Welcome to the lecture Digital 3D Documentations in Archaeology. In this lecture, we will look at how we can apply our previous knowledge of 3D documentation to the underwater sector, what differences there are, and how we need to expand our toolbox of different solutions. Here we see an overview of the topics we want to discuss in this lecture. This should help us later to find the individual topics more quickly. Let's start the topic with a general look at the use of underwater vehicles such as mini submarines. In the field of underwater, there is currently no comparable solution that enables cost-effective underwater documentation in the archaeological field in an automated way. There are indeed systems that could perform tasks of this type at much higher costs. However, due to their high price and size, they are not suitable for every application. Especially in underwater applications, where documentation methodology is still very complex and costly nowadays, the use of videogrammetry offers great advantages due to the low hardware requirements and the flexibility and robustness of the method. However, the biggest challenge in underwater documentation is georeferencing. Reliable underwater georeferencing is still one of the biggest challenges in 3D reconstruction of underwater areas, because the GPS signal cannot be measured directly underwater. Here we need indirect solutions, which we will talk about later. For the use of mini-subs for exploration or underwater documentation in the archaeological field, we should first formulate some criteria and requirements. On the left, we see the application in salt water. Greater depths can only be explored with special underwater systems. The systems presented here are usually limited to a diving depth of 100 meters for underwater inspections with an onboard camera. If attachments with additional cameras are used, the maximum diving depth may be significantly reduced. Saltwater surveys are often only feasible from a boat and significantly increase the effort required. On the right are examples of freshwater operations. Here too it is sometimes necessary to launch from a boat as a base. Many explorations can also be reached from shore due to the long cable. As just mentioned, we make a fundamental distinction between freshwater and saltwater documentations. In freshwater, the dives and the documentation work are usually a little more relaxed. Of course, we have to make sure that the equipment is watertight, well maintained and ready for use, but saltwater attacks the materials considerably more and causes rapid corrosion and plastic elements to suffer. Further cleaning phases with fresh water should be planned, especially directly after dives. There are basically two very different application scenarios with freshwater and saltwater documentation. Since the saltwater has a greater density, the buoyancy is greater here. Both scenarios require an adjustment of the buoyancy setup. This is where tearing comes into play. Tearing refers to the process of finding a balance, if possible, between downforce and upforce underwater. A submarine that would sink due to cameras and other attachments, for example, is equipped with buoyancy bodies to maintain a minimum buoyancy. If the system should fail, it does not sink to the bottom, but comes almightily to the water surface. Subsequent dives in salt water require additional effort in cleaning and maintenance of the components, as the salt can attack the equipment very quickly and make it brittle. This drastically reduces the life of a mini submarine and should not be underestimated. A mini submarine should also only be used in very calm seas and with hardly any current, which is often not possible at all in salt water. Next, we need to distinguish whether we can reach the documentation site only from a boat or by land. The latter often has the advantage that we can prepare the base for the technically necessary interventions and ideally even have an external power supply on site. This can be used, for example, to recharge the batteries. If the documentation starts from a boat, the mini submarine should already be in a prepared assembled state, so that no screws, rubber seals or other small parts run the risk of going overboard. Appropriate preparations must be made when changing the battery, which is necessary for several dives, especially for documentation. The material must also be protected from splash water. The rough setup is set. Now we have to formulate the characteristics and requirements of the mini submarine in relation to the documentation task. If the base and documentation location are too far apart, the cable lengths must be prepared and adjusted accordingly. This will affect the duration of the dive and the maneuverability of the mini submarine and should be well considered. For example, the open ROV and blue ROV can operate up to a distance of 300 meters. The documentation task also has a major influence on the setup of the mini submarine, so for reconnaissance dives, the already existing onboard cameras can often be used. If a 3D reconstruction is the goal, we have to prepare attachments for additional cameras. In order to achieve mobility and the longest possible recording time, it is advisable to use so-called action cameras, such as the GoPro. The camera is often accompanied by the time limit for a dive. Ideally, the blue ROV can dive for up to 2 hours, but the GoPro can work and record for a maximum of 45 minutes, and at low water temperatures for much shorter. Georeferencing underwater is still a challenge, as it is not easy to receive GPS data underwater. Long waves are the only electromagnetic waves that can propagate in water down to a certain depth. Therefore, only long waves with an extremely low frequency of less than 30 kHz are used in mini submarines. As GPS signals are emitted in the frequency spectrum of over 1000 MHz, self-localization underwater is therefore only possible with indirect solutions. For example, a GPS position measured above water can be used to derive the position underwater using a rod solution. Many different solutions were also developed and investigated in the Archaeological project. First of all, we want to deal with the safe handling of mini submarines. There are also important safety aspects to consider when using a diving system for underwater documentation. Protecting the electronics from water and protecting the site are the two most important aspects of safe handling of mini submarines. First, underwater systems are equipped with electronics and batteries. Contact with water can lead to the complete destruction of the system, including explosions. Second, an underwater system can permanently damage sites and finds. Apart from the fact that flora and fauna in the underwater area must also be protected and not disturbed during documentation. Knowledge of spawning times and consultation with the relevant authorities are also very important here. Regardless of which legal regulations apply at the documentation site, the following rules should always be observed, analogous to the rules for aerial surveys. First, the documentation area is secured as well as possible, and all parties involved are informed about the planned dives. Second, the pilot must not be distracted during the dive and should always know the approximate location of the dive system. Third, a co-pilot should at least be present to shield the pilot from any external influences and to take over communication if necessary. Then, diving may only be carried out in a relaxed, concentrated and healthy state without the influence of drugs. It also applies that diving in busy waters must be made safe. Another important point is that diving is prohibited in nature reserves or other quiet areas. These rules should be comprehensible and should actually be self-evident for everyone. In addition to checking the tightness of all potential water inlets, preparations for a dive also include greasing rubber rings. Cameras and diving lamps in particular often have small sealing rings that should be greased before a dive. A safe dive is only possible with well-maintained and well-tended components. Post-processing includes cleaning all components with fresh water, especially when documenting in saltwater. It is also important to ensure that the components have been dried for transportation. It is clear from the previous slides that many steps are necessary before, during, and after a dive. The use of digital or analog checklists is standard for every dive. The same duty of care applies here as when handling multicopters. Various checklists and fail-safe scenarios have been developed, expanded and adapted for our so-called MANIO diving system over numerous documentation campaigns. You can download them from the publisher's webpage. Here we see an overview of the checklists for a complete dive documentation. First, preparing the system for the dive. If a pressure test fails, there are various ways to react. If these do not help, the dive is aborted. The same applies to the sensitive control software of the mini submarine. When the diving system is ready, the first dive can be started with the aim of recording. The data is then backed up, batteries are changed, and the mini submarine is prepared for subsequent dives. The preparation for a repeat dive is less time-consuming than the first dive. At the end of the documentation, specific work processes must be carried out, including disassembly and transportation of the system. The checklists are printed out and laminated and are available in sufficient quantities with the documentation. They are ticked off and filled in with waterproof pens. In addition to the checklists, a diving log must be kept. We can see an example of the use of protocols and checklists during the campaign in Veruda in Croatia. Left above, we see the team meeting on site. Everyone involved knows what task is pending and what is planned. Below, we see the preparation of the supporting snorkeler, who directly monitors the recording. On the right, careful logging and the use of checklists for the safety of recordings, equipment, and participants is absolutely essential. Let's take a look at what underwater systems are available and how we want to define the differences between the systems in the descriptions. Let's start by talking about the names of underwater systems. Underwater systems that are cable-based are often used in the offshore sector and are referred to as remotely operated vehicles, or abbreviated to ROV, although there is no reference to underwater use in the name. The correct technical abbreviation is therefore Remotely Operated Underwater Vehicle, respectively ROUV. Underwater systems that do not have a cable solution can be referred to as Unmanned Underwater Vehicles, or UUV, in the same way as UAVs. If these systems are controlled semi-autonomously or completely autonomously, we refer to them as Autonomous Underwater Vehicles, respectively AUV. The table in the middle shows the four designations with abbreviations once again. On the right, we see three different underwater systems, with the Neptune SB1 underwater system, which can be seen on the left. We have a device from the toy sector that looks like a submarine, but can only be used at short distances and only just below the surface of the water due to the existing radio connection. In the middle, we see the 2017 version of the OpenROV, a rather lightweight underwater system that reacts sensitively to attachments such as cameras. Right. With the blue ROV, we have a system that is very well suited for additional attachments and is able to be safely controlled with several cameras and additional diving lights thanks to its more powerful motors. In contrast to the OpenROV, the blue ROV is being further developed and is already available in version 2 with numerous useful extensions. We will take a look here at the lightweight OpenROV in the context of archaeological documentation. With the lightweight OpenROV underwater system, professional documentation recordings in fresh and salt water are easily possible. The system has a weight of approximately 2.6 kg, can dive to a maximum depth of 100 meters, and offers open source software solutions for controlling and processing the available sensor data. With the LiFePO batteries, an operating time of almost 3 hours is possible. Installing and maintaining the system requires skill and care. Especially after saltwater use, the parts must be thoroughly cleaned, all sealing rings must be re-greased, and require special care. The first uses were very promising, but also revealed some limitations. It was clear that there was still a lot to be done, especially in the areas of usability and reliability of the recordings. Before we could start archaeological documentation, we had to practice a lot with the system and prepare the components for the task. Here we see the operation in Kamenz in a quarry. At the bottom left, we see the biggest problem when using a mini submarine with a 300-meter long cable. Cable management was therefore necessary in order to move the underwater system forwards and backwards in the same way as a multicopter in a grid shot without tangling the cable. As the OpenROV was only available as a kit at the time, it first had to be carefully assembled. Although it has an internal front camera, a GoPro in the Hero 3 version had to be mounted underneath the device for professional recordings. 4 diving lights, each with an output of 860 lumens, were also fitted. After mounting the camera in a special housing, a maximum diving depth of 60 meters was still possible. However, every modification makes it necessary to re-tear the system and, for example, equip it with additional buoyancy bodies or weights. One important rule applies here in particular. A well-teared system is the necessary basis for every underwater documentation. Once the system is teared and ready for use, it can be used for recordings in the same way as the recording strategies we know from multicopters. In contrast to the aerial flights, however, the 100-meter-long two-pole twisted copper cable must be carefully wound and unwound during the recording. This makes underwater filming very time-consuming. In order not to reduce maneuverability due to the high tensile force of the cable in the water, a supporting snorkeler must relieve the cable in the water just before the open ROV. This means that with the pilot, the logger, the snorkeler, and the person carrying out the cable management, at least 4 people are required to put the system into operation. At the picture, we see the use of the underwater system with the Lower Saxony Institute for Historical Coastal Research at the Zwischenahner Meer in Lower Saxony for sounding in the shallow water area in 2016. At least 4 people are needed for a successful survey. All cable-based systems require good organization of the existing electrical cable between the mini submarine and the base station. In the case of the open ROV, the cable is a thin and very sensitive 100-meter-long cable that transports the sensor data in one direction and control signals in the other. To protect against finds in the water, it may be advisable to fit small, lightweight buoyancy bodies to the cable. In addition to the buoyancy bodies, which consist of lightweight plastic strips filled with air, a robust red rope has been installed to take the force from the electric cable. This means that the mini submarine can also be pulled ashore completely via the cable if required. This modification has the advantage that the cable is always on the water surface, but has the disadvantage that more power is required for navigation due to the greater pulling force. This means that the open ROV cannot navigate a full distance of almost 100 meters without additional support. For this reason, a support diver or snorkeler is required near the mini submarine on the cable to relax the cable and thus enable navigation. Here you can see a dive with Egbert II, a modified open ROV in Veruda in Croatia during the documentation of an exposed shipwreck at a depth of approximately 6 meters. Here, the cable from the base to the mini submarine has been released by a snorkeler. This makes a smooth dive possible. Ideal recording strategies that we need for a successful 3D reconstruction, with its overlaps and intersections, correspond to those that we have already motivated and learned about multicopters. For 2 reasons, implementing these theoretical strategies in practice in underwater scenarios is not quite so easy. First, purely cable-based underwater systems often involve very complex cable management, where the cable has to be continuously wound and unwound. Second, localization of the mini submarine is only possible indirectly and therefore often very imprecisely. For the second reason, underwater recording strategies should have significantly narrower paths and higher redundancies. With a double grid strategy, cable management is significantly more complex for one of the recording directions. It makes sense to record the better direction much more closely and therefore more redundantly, and to interpret the more complex direction as correction paths for the data. In the further course of this lecture, we will look at the stable and powerful blue ROV. For the development towards a semi-autonomous documentation system, the basis of the open ROV was replaced by a blue ROV as part of the Archaeonautic project in 2017. There are several reasons for this. On the one hand, the blue ROV is designed with a much more stable frame, allowing for more attachments, and is much easier to navigate via the more powerful motors due to its good diving characteristics. This means that additional attachments such as brackets, cameras, and diving lights can be installed. On the other hand, the blue ROV promises more individual solutions thanks to the larger user and developer community, and will hopefully be available on the market for longer. Although the onboard cameras already present in the OpenROV and BlueROV can be used very well for underwater exploration and control, they are less suitable as a starting point for 3D reconstructions. Here it is necessary to attach a version of the GoPro Hero, for example, which can perform well underwater. As a camera underneath the mini submarine seems to make the most sense, similar to a multicopter flight, a mounting device must be prepared. To prevent the camera from resting on the ground on land, additional foot sections should be fitted or the side sections extended downwards accordingly. The underwater systems presented each have advantages and disadvantages and can be conceptually adapted. From a cable-based system or ROV based on the BlueROV, we will develop and motivate a cable-reduced, radio-based system as defined as UUV in the following slides, which is suitable as the basis for a semi-autonomous system, respectively AUV. Internationally and especially in Europe, there is a signal flag that indicates a diver underwater in shipping traffic. In order to avoid collisions and accidents, it makes sense to also display this flag on the buoy. To avoid misunderstandings, both flags can be mounted so that they are clearly visible. On the left, we see that the flexible mounting mechanism also allows large arm booms with many cameras. In this case, 5 GoPro Hero 4 cameras capture a pile-dwelling settlement in Lake Mondsee in Austria. On the right, the radio buoy is equipped with 2 signal flags. The so-called red and white flag at the top shows the international standard and the diver or alpha flag at the bottom. The mini submarine has a relative position system as standard and thus enables the acceleration forces for the pitch, roll and yaw axis to be assigned. The information obtained about the orientation of the UUV together with its speed is used in an observation model to determine the position of the mini submarine relative to the known position of the buoy on the water surface. Left, in a favorable recording situation in which the mini submarine is constantly moving in one direction for a certain period of time, the GPS position from the buoy can be used to determine the exact position of the mini submarine underwater. On the right, based on the known cable length and the determined diving depth, the position and orientation of the UUV underwater can be derived. Using the Pythagorean theorem, we can estimate the position of the mini submarine in a very simple way. As parameters, we need the diving depth, the cable length between the mini submarine and the buoy, and the situation that both are constantly moving in one direction for a certain time so that the cable is fully extended and tensioned. In these situations, we can therefore determine the position of the mini submarine relatively well. A ping sonar from Blue Robotics was installed for further data collection, localization and determination of the subsurface conditions. This sonar has a working range of 0.5 to 70 meter. Within this range, it can scan the subsurface with a scanning angle of 30 degrees and a scanning speed of 115 kHz. This makes it possible to measure the depth between the bottom and the submarine directly during the journey. Left above, the deeper Pro sonar can be seen as a black sphere. Below, the ping sonar is mounted on the BlueROV. To the left, a fully functional grab arm has been retrofitted, with which samples can be carefully taken. On the right, we see the result of the depth measurements of various dives at the reservoir in Oberwartha in Germany. On the right, we see the result of the depth measurements of various dives at the reservoir in Oberwartha in Germany. Here, dark orange means up to 1 meter depth, yellow up to 10 meters, green up to 20 meters, and blue up to 30 meters. The deepest point of the reservoir was measured at 29.132 meters.